This will be the third time I've attempted to springcast this talk. Hopefully now the issues will be fixed. We begin, though, historically, with a gentleman named Michael Faraday. If we go ahead just a little bit and you look at this blurb here, you can see he's a 19th century physicist and chemist. He's probably the most important experimental physicist and chemist of the 19th century. He made so many contributions in both fields. We would not be where we are today in the 20th century were it not for some of his insights and discoveries regarding electric motors and electric generators and transformers, for example. What is not often known is that he was a very devout Christian man, kind of the Quaker type of perspective. And of course, this little blurb here says that he was influenced by religion. And that's always the generic way, oftentimes, to speak about Christianity and lumping it together with all the other faiths. Please keep in mind, of course, that one big difference out of many between Christianity and all of the other faiths is that Christianity is about a about a relationship. It is not just a religion. I should also point out that, contrary to some people's opinion, not all faiths point in the same direction. In fact, all faiths are mutually contradictory. Either they are all wrong, or only one of them is mostly right, as far as we understand it. Because they are all mutually contradictory. We need to keep that in mind. One way in apologetics to look at all of the different faiths is to look at their explanatory power. At least that's how a scientist might think about it. And personally, I am absolutely amazed by how well the ultimate reason for why things are the way they are in this universe is explained by God's Word and biblical Christianity. Well, going back, we have this word induced voltage and then the word inductance, which obviously means something to do with the amount of inducing. You might recall in static electricity, chapter 15, we talked about directly charging an object like a balloon or a metal sphere called conducting or conduction. And we talked about indirectly charging something by bringing a charged object close to, but not actually touching, a balloon or a metal sphere or something else. That was called induction. This is kind of the same use of the word. You can establish a voltage by directly hooking something up to a battery. Or you can establish a voltage indirectly. You can induce that voltage without having a battery at all. And that's the discovery of Michael Faraday, one of many. And that's what I hope you'll begin to understand as we go through this screencast. Now, we begin by looking at this picture at the bottom of the page. We have a vocabulary word, coil. Another word for a coil is one or many loops of wire, or the technical term would be a solenoid. And here you have two loops of wire. You have the primary coil, which is the one that is ultimately connected to a battery, and you have a secondary coil not connected to the battery that is on the right. You don't actually need the iron ring, but the iron ring helps to enhance the effect that I'm about to explain. Now, the picture shows a car battery. I don't know why, it's not necessary. A car battery would probably produce so much current it would fry the wires. Nevertheless, if we had a D-cell or a AA battery or something like that, and we had a wire connected to it, you'll notice that the wire leaves the positive post, goes through a switch, and then the wire continues after the switch over the top of the iron ring, goes around and around the iron ring as it comes towards you in the picture, and then underneath the iron ring goes back to the battery. Of course, if we're talking about voltage, we would say it goes back to the battery without any energy left per charge. Plumb tuckered out is the phrase I've been using from the South. And so what you should recognize here is this is nothing more on the left side of the picture than an electromagnet. You close the switch, current goes through the wire. When you have moving charge going through a wire, you create a magnetic field, an electromagnetic field, because electricity is causing it. You open the switch, and your magnetic field ceases to exist. In other words, the act of closing the switch causes a magnetic field, an electromagnetic field, to spring into existence, to expand into space, reaching some set effect in the space around the wire, as dictated by the voltage of the battery and the mechanics of the device. It's enhanced because there's an iron ring going through the coil or solenoid. The wire is insulated, so no electricity from the wire makes it into the iron ring or coil. Now, the next thing you should notice on the right side is a second solenoid, and the second solenoid is connected to either a voltmeter or an ammeter. It can measure either an induced voltage or an induced current. And the reason I'm saying induced is because it's not directly connected to the battery. The more turns of wire, the greater this effect is going to be. Now, the reading on the meter says 0. Nothing is going on because there's no moving magnetic flux lines. As soon as I close the switch, for a moment, the magnetic field expands into position. And that expanding magnetic field, those expanding flux lines, creates a movement of a magnetic field around the iron coil, which therefore is going to induce a current in the coil. Remember, anytime you have a conductor, in this case the iron loop, which in a sense could be many turns of wire, but it's just one in this case, it induces a the turning on of the battery, connecting it to the primary coil. That current creates the magnetic field. The expanding magnetic field induces a current in the iron ring. That current in the iron ring, as soon as it begins to move, only during the time that the magnetic field is expanding, induces current in the secondary coil because of the magnetic field that is created by it. And that current then can show up on our meter either as voltage or amps. Please note again that the primary coil and the secondary coil are not electrically connected. The expanding magnetic field induces an effect on the iron ring. That effect on the iron ring induces current in the secondary coil. That's why we say it is induced, because it's not directly connected. An induced EMF, or voltage, is produced in a secondary circuit by the changing magnetic field created by the expanding magnetic field when you turn the circuit on. If we were to open the switch, again, you would have a moment of induced voltage because the magnetic field would be moving. It would be collapsing to 0. So remember this. You turn the circuit on, we have an expanding magnetic field. Once it expands into position, there are no magnetic flux lines that are changing. Voltage goes to 0. You open the switch. In other words, you turn the circuit off. The magnetic field collapses, momentarily producing moving flux lines, momentarily, ultimately inducing a voltage. Now, in this situation, we can recognize several things. That is that the strength of the magnetic field is going to be dependent upon how many flux lines. The number of magnetic flux lines dictates the strength of the magnetic field. Also, the amount of the flux lines affects the magnetic field, and the number of wires that are in the vicinity of those moving flux lines affects the magnetic field. Letter B is the letter that we use to represent the strength of the magnetic field. You'll notice also the little perpendicular sign below the letter B, meaning that as long as you have your wires, and the wires in your loop, which could be a circle or a square or a rectangle, it has a cross-sectional area, as long as those wires are perpendicular to your flux lines, you're going to get your maximum magnetic field strength. If it's not perpendicular, then you have to throw a cosine theta in there. So in other words, if your loop of wire, if the area of your circle, your ring of wire, or your rectangle of wire that is in the magnetic field is parallel to your flux lines, your cosine theta goes to 0, and therefore your magnetic field strength will be 0. Now, the flux lines was represented by that weird-looking Greek symbol, which is the 21st letter of the Greek alphabet called phi. It looks like the capital letter I with a circle around the middle of it. I have it highlighted in blue from my previous attempt to screencast. The flux lines are measured with the international metric unit called the Weber. If you were to take these Webers, these flux lines, and divide it by A, you have Webers per meter squared, which is the strength of your magnetic field. The more Webers, the more flux lines, the more lines representing the magnetic field you have squashed together in the region of space about your wires, that would imply a stronger magnetic field. It's almost like we're talking about the magnetic field or flux magnetic field density. At the bottom of the page, we have what looks like a window, which is actually a loop of wire. It could be one wire in the shape of a rectangle. It could be 1,000 wires in the shape of a rectangle, but it would be a simple way of representing a solenoid, a coil of wire. If your flux lines are moving perpendicular through this window, so to speak, the more flux lines going through the window, the more you have a magnetic field in the vicinity of your wires, which is the window, and you have your maximum magnetic field strength. But if you're coming in at an angle, theta, then it's going to be reduced a little bit. And then, of course, if theta went all the way so that your window is running parallel with the magnetic flux lines, then your magnetic field strength would be 0. In this next page, we should mention the fact that, once again, since we're interested in the cross-sectional area of the solenoid or coil of wire that is in the magnetic field that is experiencing the changing flux lines, we have to be able to calculate that area for this equation. And some of you still are struggling, strangely enough, with correctly calculating the area, which of a circle in this case is pi r squared, where r has to be radius and it has to be in meters. I noticed in the last test, some of you still missed this. Now, this next section, Faraday's law of induction and Lenz's law, is going to be very important for the rest of the chapter. Faraday's law of induction, I think you're already getting a sense of. We can induce a voltage or a current in a secondary coil as long as it's in the vicinity of a moving magnetic field. That moving magnetic field could be an electromagnet that is being turned on and off, so you would have an expanding and collapsing magnetic field creating the motion. Or you could hook up your electromagnet to an alternating current source, that's chapter 21, in which case your current would be reversing direction 60 times a second in the United States. And that would create the moving magnetic flux lines. Or in this picture, you can see you can take a permanent magnet, like a bar magnet, and physically move it back and forth, creating a moving magnetic field. So therefore, you would have a wire experiencing moving magnetic flux lines, changing magnetic flux lines. And you can induce a current that way. Lenz's law is the hardest thing to explain in this chapter. And there are some really cool demos of Lenz's law where you drop a strong magnet through a narrow copper pipe. And that copper pipe, of course, is not magnetic, so the magnet will not stick to the side of the copper pipe. But as the magnet moves through the copper pipe, you'll see the effect of Lenz's law, and I'll leave it to you to find a video to this effect, at least for the time being. It's one that I would do in class at this point. What would happen is the magnet would move or fall under the influence of gravity, but very, very slowly through the copper pipe. Not because of friction, but because a current will be established in the copper pipe as a result of your strong magnet falling through the copper pipe. And that current will create its own magnetic field opposing the permanent magnet that is falling through it. Let me explain by using the picture here at the bottom of the page. Lenz's law, explain it to somebody else, you know that you'll understand it. So here we have picture A at the bottom. We have a hand that's moving this permanent magnet from the right to the left in the direction of the red arrow. Therefore, the flux lines are moving relative to the stationary wire that's hooked up to this ammeter. In this case, this meter is measuring an induced current, not an induced voltage. Because the hand is moving, the magnetic flux lines are moving. Therefore, the wire is in the field or in the vicinity, in the region of moving magnetic flux lines, and it induces a current in the wire. That's Faraday's law of induction. But Lenz's law allows us to predict what will the direction of that current actually be. Now, the purple arrow with the letter I represents the direction of the current. How can we predict that? That's Lenz's law. So here's what you do. If you recognize that the North Pole is moving to the left, Lenz's law says the current in the wire connected to the meter will travel in a direction in order to create a North Pole going to the right, in the opposite direction. It's kind of like Newton's third law. For every action, there's an equal and opposite reaction. If the North Pole is going to be going to the left of the permanent magnet, then the current will be induced to create an electromagnet North Pole pushing back to the right. Which direction will that be? If you take your right hand, use the right hand rule, another one, we have had several in the last chapter, and if you let your fingers follow the direction of the current, which would require you to have your fingers coming out of the page above the magnet and going down into the page below the magnet, you'll notice that your thumb has to point to the right. That's why they chose this direction for the current, because your thumb represents the North Pole of the electromagnetic field produced by the induced current. Again, we have two magnetic fields. The magnetic field of the permanent magnet that's moving to the left, and the induced magnetic field as a result of the induced current, whose North Pole by Lenz's law, has to push to the right, be to the right. And the way you accomplish that is by having the current going in the direction of the purple arrow, coming out of the page, going towards the bottom, going into the page at the very bottom, coming back around out of the page above and into your face and back around in the direction of the purple arrow. Your right hand rule, if your fingers are curving in the direction of the current, has the thumb going to the right. Now, in the middle picture, picture B, your hand is not moving. No moving magnetic flux lines, no induced current. In picture C, now we move the hand to the right. The moving magnetic flux lines then induce a current in the wire, but this time the current has to go in the opposite direction because of the fact that if your north pole is moving to the right, the current will be induced in the wire to create a north pole going to the left. So if you take your right hand and you have your fingers curling in the direction of the purple arrow, you'll notice your thumb is pointing to the left. It's not uncommon on an AP or any other test like the one that you'll get over this chapter, where you have to use your right hand rule to predict the direction of the current as a result of the moving magnetic field. And just a heads up about chapter 21, alternating current. If your hand is going back and forth, left and right, you would actually be creating an alternating current. Positive, negative, positive, negative. Also, as hopefully you realize, you can increase the amount of current that you are inducing, or you can increase the induced voltage by increasing the number of turns of wire. This script letter E, which we could have used in capital print E, or we could have even technically used the letter V for induced voltage, is directly proportional to N, where N is the number of turns of wire. Another thing that you should have anticipated is the faster I move my hand back and forth, the faster I'm changing the flux lines. In other words, these changing flux lines, that's the delta phi, divided by delta t, the more those flux lines change per time, the more the induced voltage or induced current will be. And of course, as delta t gets smaller and smaller, your change in flux lines becomes greater and greater, inducing a greater voltage. Now, what you might not have noticed, and this is where people lose a point on test questions all the time, notice the negative sign in equation 20.2. That negative sign is because of Lenz's law. That negative sign is like the equal and opposite. It's the pushback. Here is an example of solving this problem. Again, the negative sign in the answer, negative 5.06 times 10 to the minus third volts, based upon a solenoid of 25 turns of wire, a magnetic flux of 1.62 times 10 to the minus fourth Webers, and a speed, or a time, I should say, of 0.8 of a second. Now, there are three examples given here of this induced current and Lenz's law. And again, this is challenging to explain verbally. Here's example 1, upper left-hand corner. You have two artifacts, two objects. You have a vertical wire going from the bottom to the top, pictured in gray, and you have what looks like a window or a gray rectangle, which is actually 1 or 100 or 1,000 turns of wire. It is my solenoid. It is my loop. If you can say a loop is rectangular. Now, let's focus on the left side. Imagine that you have a circuit connected to this wire that's moving, that's vertical, and you turn on the electricity in such a way that the current flows from the bottom of the wire, where the positive post of the battery would be, towards the top of the page, and then back around eventually to the negative post of the battery. As soon as you turn the circuit on, current will go through the wire in the direction of the red arrow. If you take your right hand and you have your thumb pointing upward in the direction of the red wire, and you should be doing this right now as I speak, you'll notice that the natural curvature of your fingers curves behind the wire, inside or below the page. It comes out into your face on the left side of the wire. It flows across the top of the wire above the page, and then in the window, it's going down into the page, into the direction of that green arrow. That's the magnetic field established about the wire because current is going through it. So the point right now is that in where the window is, the magnetic field is going into the page. All right. Now let's look at the window, which is actually a solenoid or a rectangular wire. What direction will the current go that is induced in that rectangular solenoid? And the answer is Lenz's law. If the magnetic field about the vertical wire is going into the page on the left side of the window, that means the induced current will travel in a direction to create a north coming out of the page. A magnetic field coming out of the page in the vicinity of the window. And in order to do that, that means the current has to flow upward on the right side of the window, the right side of that solenoid. And again, take your right hand. If your thumb is pointing upward, representing the red arrow, you can see that, just like before, the magnetic field is going to be going into the page on the right side, from right to left, underneath the window, and up at you, into your face, inside the window, in the opposite direction of the magnetic field created by the current in the wire. Equal and opposite, hence the negative sign, according to Lenz's law. Let's look at another example. In this case, instead of having electricity going through a wire to create a magnetic field, we have a permanent magnet. If my permanent magnet is moving from left to right, that means the North Pole is traveling toward the right across the face of the page, and we have moving magnetic flux lines because the magnet is moving. It's going to induce a current in the ring. What direction will the current go in the ring? Lenz's law tells us if the North Pole is going from left to right of the permanent magnet, then the current will travel in the direction of the ring to create a North Pole going to the left. What direction will that be? Well, the picture tells you. Follow the purple arrow. Take your fingers, pretend it's the current curving in direction of the red arrow, and your thumb would naturally point to the left. So if the North Pole of the permanent magnet is going towards the right, then the current will create a North Pole pointing to the left. What does that magnetic field look like? We'll come to picture B. Picture B is just the loop. We're not showing you the moving magnet here. The green arrows in this case are the induced magnetic field that the current in the wire is creating, and the arrows are pointing towards the left in the middle of the ring, in the opposite direction that the green arrows of the magnetic field of the permanent magnet are creating as it goes towards the right. You'll have to give me some feedback if you understand that. Now, all this blue thing here somehow got highlighted, and with the limited software that the textbook company that is allowing me right now to access the textbook online, it does not allow me to get rid of all that blue highlighting. Now look at the picture at the bottom of the page. Lenz's law, example number 3. It's very much like the picture at the top of the page, but the difference is at the top of the page you have it had a permanent magnet that was moving. In the bottom of the page we have an electromagnet. In the top of the page your permanent magnet was being moved by a hand to create moving magnetic flux lines. In the bottom of the page, your moving magnetic flux lines will be created by an electromagnet when you turn it on and when you turn it off. We're accomplishing the same thing, creating moving magnetic flux lines. Now, look at the picture at the bottom. Picture A. You have a wire going from the battery. Those two vertical green lines is the symbol of our battery. It goes out the positive. It travels up towards the iron cylinder or ring that enhances the upcoming effects. The wire goes over the top and underneath and around and begins to go around and around and around some 7 times, moving towards the right. It exits the coil underneath the rod, underneath the rod, where it goes back to the switch. I hope you understand that description. Now we can anticipate where the north pole of this electromagnet enhanced by the iron rod is going to be. If you take your right hand, follow the direction of the wire out of the battery from the positive side, your fingers would naturally curl over the top of the iron rod, and your thumb would naturally point to the left. That means that when we close the switch, we will be creating an electromagnetic field whose north pole will be to the left. So we close the switch. As we close the switch, a magnetic field springs into existence. The magnetic flux lines expand to some limit, dependent upon the voltage of the battery and the mechanical pieces of the device. While the magnetic flux lines are expanding into position, those moving flux lines induce a current in the orange coil. In picture B, we now have a magnetic field about the coil. And that magnetic field, as it is expanding into position, induces a current in the orange loop. What direction will the current be? Take your fingers and try. Curl your fingers in one direction around the ring, then curl your fingers in the other direction around the ring. Which one is going to create a north pole going to the right? Which one will have your thumb pointing to the right? And you can see that if your fingers are curling in the direction of the purple arrow, your thumb will be pointing to the right in opposition to the fact that the electromagnetic field of my electromagnet, when I turn the battery on, is going to the left. We explained that a minute ago. Lenz's law says the current will be induced in the orange coil to move in the direction to create its own electromagnetic field in opposition to the electromagnetic field created by your electromagnetic magnet in the first place. So we have two electromagnetic fields. The electromagnetic field created by the electromagnet connected to the battery with the solenoid, the wires going around the iron core, and the induced electromagnetic field created by the induced current in the ring, the orange coil. Notice the word coil is used in multiple terms. You've got the original coil, we call it the primary coil, the 7 loops of wire wrapped around the iron ring connected to the battery. And you have your secondary coil, here represented by this this orange colored ring, which would be a conducting material. Now, another thing, moving to picture C, you should notice, is as soon as I turn the switch off, my electromagnetic field of the primary coil collapses to zero. And when those magnetic flux lines are collapsing to zero, it induces a current in the orange coil, the secondary coil, and this time the current goes in the opposite direction. So the only time we have induced current in the orange coil is when we close the switch, turning the electromagnet on, and when we open the switch, turning the electromagnet off. In between, no moving flux lines, therefore no induced current. Again, the only time we have an induced current in the coil is the moment you turn the switch on and the moment you turn it off. In between, there are no flux lines moving because the magnetic field is not expanding or collapsing. We have 3 examples of this, practical examples. Practical example number 1 is a ground fault interrupter. If you live in a newer house, chances are you have one of these in the outlet or 2 closest to your kitchen sink, in the outlet closest to your sinks in the bathroom, in our lab and in our classroom. Every outlet that's near a sink or near water also has a ground fault interrupter. It has a little button to press. And the idea is water can cause electrical things to short circuit. Or frayed wires can cause shorts as well. In either case, you'd get a sudden surge of current following the path of least resistance, which hopefully is not going to be through you, because that would be quite a jolt, and you would hate it when that happens. And so if you were to have a surge of current going through water or a frayed wire that you might inadvertently touch and the electricity would go through you, that surge of current would be a changing current, which would create a changing magnetic field, which could be sensed by a sensing coil. And that little bit of induced current in the sensing coil, because of the sudden surge of current that's taking place in a fraction of a second, would be enough current to turn a switch, to throw the circuit breaker off, to disable that switch, that outlet, I should say, so that you would not be electrocuted. Example number 2. I've played an electric guitar before, and no, I did not play with Jimi Hendrix at Woodstock, though my hair was about that long at the time. That's an interesting thought. Here, the interesting effect, though, is that if you pluck on a steel wire, you are creating a moving wire. And that moving wire, if it's got electricity through it, can create moving flux lines, which can be picked up by a coil of wire that can send a signal to an amplifier. And a very important application is every now and then, tragically, a baby might have an interruption to its breathing. We don't always know the biological cause for this. We call this the sudden infant death syndrome. And of course, we're trying to avoid a baby dying because it stops breathing for reasons we might not know yet. And so if we think this might be an issue, we can wrap a coil of wire around the baby. And this coil of wire is in the vicinity of a secondary coil that's hooked up to a very low voltage power supply. So as the baby breathes in and out and the chest goes up and down ever so slightly, you have these moving wires in the vicinity of a magnetic field. If the baby were to stop breathing for some reason, then the motion would stop, the electric flux lines would go to zero, and this could be used to trigger an alarm to go off. And the apnea then could be sensed, and hopefully you'd be able to start the baby breathing again, sometimes just by massaging the chest. And that concludes our first video cast, and I hope it works.